So I'm happy to have Professor Nguyen from National Taiwan University. And Tien's research focused on partial differential equation. I guess arising from physics, biology, chemistry, and so on. So let's welcome speaker.
Thank you, Tien, for your introduction, and thank you very much for your kind invitation to encourage you for the seminar today. And thank you on the audience today. It's so impressing me that many people come to my seminar. And thank you for your efforts to other students to come. It's much better than NTU, so honestly I can say. Okay, so today I will talk about a subject I work on in the last few years, the so-called singularities in the Keller-Segel system. So before I start the talk, I want to explain the title of my talk. So in the title of the talk, you see there are two things. The first thing is singularity. So what does it mean, a singularity? So formally, when you study PDAs, you have initial data. And then you start with a perfectly smooth initial data. And after some finite time, some sort of unbounded happens in the solution or in its derivative. So the formally explanation what the singularity. So the singularities I want to talk today is the blow-up solution. So the blow up in finite time. And the Keller-Segel system. So I will write it. Should be here. So we have two things. The singularity, I mean today, which is the finite time blow-off. So in the sense that a subnorm of the solution is go to infinity at t approach some capital T. And here the Keller-Segel equation, so Keller-Segel, it's a couplage of equation, the parabolic. So each one is just a linear heat equation, and we have the nonlinearity. So capital phi sub u is a Newtonian potential is defined by the following. And we consider here in the domain, the whole domain RD. So 4D is greater than 2. And when we solve this system, we need to have the initial data U0. Right. So this is the explanation of the title of my talk today. Okay, so we have this is the plan. So firstly, I will introduce what the blow-up phenomena happen in the Keller-Segel equation and what it contribute to the development of the blow-up analysis and what so-called the resolution of solution with self-similarity. And I will introduce what the main objective of my talk today. And when we study the Keller-Segel equation, we need to distinguish between the dimension. I mean, the dynamic, the blow-up dynamic of the solution is quite different, depend on the dimension. So we have the different blow-up dynamic in dimension 2. Sorry. And we have a completely different dynamic in dimension d greater than 3. Okay, so look at here. And I formally explained to you that we start with perfectly smooth initial data here. And after some finite time, I mean at first, because the effect of the diffusion, we have the solution is diffused. But because the effect of nonlinearity here, the solution tend to concentrate here and become unbounded in finite time. And this one you can see clearly from this simulation I make here. And you can see clearly that we have start from the perfectly smooth input data the solution become unbounded in some finite time. Okay, so what we are interested in is that the structure of the solution near the singularity, near the plow point here. And in the last 30 years, so what we are interested in is that whether or not there are plow solution within the finite energy class. So this is a Keller-Segel equation I just wrote here. And we have the classical model. The first one, the nonlinear heat equation, is the most studied one. And we have the counterpart, the nonlinear wave equation, and we have the nonlinear Schrodinger. And we also have the open question for the 3D Navier-Stokes equation, whether or not we have the finite time Plouf solution for the incompressible 3D Navier-Stokes equation. So it's still open right now. And when you look at those models, those classical models, we have a common similar structures, the so-called the self-similarity structure. So in the sense that we have x0, t0 at physics, and lambda is a positive parameter. And when you define this function, and this function is still satisfies one of these models. So with approximate choice of alpha and beta, so alpha and beta is some positive constant. And when you look at the solution of this form, we will have the traveling wave solution, we have the forward, backward, self-similar solution, or we have the steady state solution. Okay, so now what I want to introduce is so-called a single Plouf with asymptotically self-similar in the sense that, so the solution is here in the lambda, the parameter lambda here is no longer constant, but it depends on time. And it's so-called the length scales of the solution to characterize the concentration zone of the solution. So for the Keller-Segel, so we look for the solution of this form. So it means that they can decompose at the leading order term by some nonlinear object, and the lambda t here is the length scale, which is unknown, and plus some radiation epsilon. And similarly for the nonlinear heat, nonlinear wave, and nonlinear Schrodinger equation. And we also want to look for a Plouf solution for 3D Navier-Stokes equation of this form, but it's still an open problem. And when you look at here, we have two main unknown objects. The first thing is W, is so-called a nonlinear object. It can be the stationary state, traveling wave, etc. And we have the lambda, which is length scale, we need to determine. And we have the epsilon here, the radiation. How can we control it so that it doesn't affect the leading dynamic of the solution here? And then to determine the two main unknown, W and lambda, we since 1990, so almost 30 years, more than 30 years. We have many techniques based on renormalization, modulation, or perturbation analysis, or matching and synthetic expansion. And today I want to focus on a new method we developed in the last 3 years, so-called spectral analysis of the multiple scale problem to construct a finite time Plouf solution within an energy class. Okay, so this is an example of single Plouf for the 2D for the Keller-Segel equation. So this work is done, it should be 3 years ago. So what we did is that we are able to construct initial data so that the solution plows up in finite time and can be decomposed of this form. So where the leading term is given by W, the nonlinear object, is the stationary solution, where the total mass of capital W equal to A pi. And the length scale here, lambda, which is important to understand what is the concentration zone of the solution. So here what do we have? We have lambda, the length scale either given by this law. When you look at here, it looks quite complicated, but it has to be like that for the 2D case. And we have also either that the lambda, the length scale, is given by this formulation for some integers L greater than 2. So this is for the 2D case. Another example for the 3D case is that, for d greater than 3. So we are able to construct, to find initial data, of course, a perfectly smooth initial data, so that the solution can be decomposed. Here it's quite different because the nonlinear object now is the traveling wave solution, which is given explicitly given by this formulation. And here we have the length scale lambda is related to the distance capital R here. So what does it mean here? It means that if you look at the radial symmetric solution in 3D, so at first the initial data is concentrated on the surface of a surface with a distance capital R. And then when the time progresses, when t approaches capital T, so the distance, the radius of the surface is screened to 0. So that, at first the solution concentrates on the surface of the sphere and later become concentrated at only one point. So that will give you a completely different, dynamic between, the 2D case and the higher dimensional case. Okay, so what the contribution to the development of blob analysis or the development of the study in nonlinear PDEs? So when we study the PDEs, what we want to do is to describe the structure of the solution, as much as possible. And in that context, we have the so-called resolution of solutions with self-similarity. And we have the following constructor for the 2D Keller-Segel. So if we start with initial data, of course, the smooth initial data, where the total mass of the solution is between 8 pi and 16 pi, then the solution is decomposed of this form, where capital W is the stationary solution and lambda, the length scale, is only given by either this law or this law. So that is what our contractors for the 2D Keller-Segel. But why we retreat it for the total mass between 8 pi and 60 pi? So in the sense that, so we may ask that what if the total mass is greater than 60 pi? So because there is a possibility to have a multiple collapse, so that will make the situation more complicated. So for that, we can only, solve this constructor for the mass between 8 pi and 60 pi. And I will show you later that for the mass is greater than 60 pi, we do have the multiple collapse solution, that the blob solution is formed by the collision of subcollapse. So for this constructor, we have up to now the only available result due to the Mac and Raphael for the critical nonlinear Schrodinger. But in their work, they couldn't obtain the formulation of the length scale lambda because they used just a purely energy estimate without using the spectral analysis, so that they couldn't obtain what a formulation of length scale lambda. And for us, what we hope is that with our spectral analysis, we hope we can obtain precisely the formation of lambda, which is given by this one. Okay, and then what is the resolution of solution with self-similarity? So in the sense that for general initial data, what we expect is that the solution can be asymptotically decomposed at the sum of multiple solutions. Here WK and lambda K can be varied. And WK is the nonlinear profile with self-similarity structures, and lambda K can be different. And epsilon is so-called the radiation that characterized by the solution of associated linear right problem. And the time here, capital T, can be finite. We have the blob solution, or infinite. We have the global solution. But to answer this question is quite difficult. So it's still, a long-term, a long-term progress to achieve this, to answer this question. Okay, so now let's come back to the question, what happens if for the 2D Keller-Segel, if we start with initial data with the mass is greater than 60 pi? And what is the collapsing phenomena? And here you see here we start with initial data concentrate at 2 points, at 2 different points, concentrate here around A pi and here a little also A pi. I place it symmetrically along the axis. And then when the time progress, by the nonlinear, the effect of nonlinearity, the solution is concentrated at 2 points, and at the same time they merge together, and that they form the collapsing phenomena. And what exactly happened here when I made the simulation? Yeah. So for the numerical simulation, we do have the collapsing phenomena. But how can we describe them? It's for us we started project 4 years ago, but at first we couldn't do it, and we just solved it this year because it took so many complicated process. But I will explain to you in a simpler way how can we adapt the strategy for the for the single plug construction to the multiple collapse construction. So my main objective of the talk is that I will first revisit the single plug construction. Oh, sorry. For the 2D case, so-called the L1 criticals, and from that I will briefly introduce you how can we make the construction for multiple collapsing plug solution that I just showed you in the simulation. And we also have the possibility of other plug pattern in the higher dimensional case. So here I should explain to you that what does it mean of the notion of criticality. So we have the criticality is coming from the scaling invariant. So we have this function defined 1 over lambda square of u of x over lambda t over lambda square. And then when you compute it, the L1 norm, so will be equal to lambda to the power d minus 2 u of lambda of t of L1. So which is in RD, we evaluate in RD. Right. And you see here for d equal to 2, we have the notion of L1 critical. And we have for d greater than 3, so-called the L1 supercritical. Okay, so let me first revisit the single plug solution, single plug construction for 2D Keller-Segel. So what we did is, in collaboration with Kolo, Goose, and Matmodis at New York University, and what we did is that we are able to construct a smooth initial data, which is a finite mass in R2 space. And the solution is plowed up in finite time and admit this decomposition, where the radiation epsilon is converted to 0 in this energy norm. And we have Q, which is the stationary solution, where the total mass equal to A pi, and the length scale is given by either this formulation or this formulation. So, what the motivation for us to obtain the result really knows in the radial symmetric case by Hero Velasquez, Swire and Raphael, and many other authors. The thing is that the existing result, it only holds for the radial symmetric case, and they cannot extend it for the complete non-radial case. And we try to use the approach to construct a multiple collapse solution, but we couldn't succeed. So that forced us to develop a completely new method based on a spectral analysis, so that we are able to complete the construction of multiple collapse phenomena solution. So that's the main motivation for us to revisit this construction. Okay, so the main idea is that we move to the self-simplest variable. So it means that we take this chain of variable, which is the parabolic scales, and then we write down the original equation. We turn to this equation. It's almost the same, but we have the extra scaling term here. And our aim is that we want to control initial data for this equation, so that the solution can be decomposed of this form, where nu here is a null parameter. But when you trace back to the formulation, it really stays in the theorem. So nu is either given by this law or even given by this law. So the construction is based on three main steps. The first one, we have to construct a good approximate solution. So at this stage, so after you obtain a good approximate solution, you are able to obtain formally the law of the plot, I mean the length scale, nu here. And also you have to know what is the profile of the solution. And then the second part is you try to control the radiation, in the sense that you try to reduce the linearized problem to a finite dimensional one. So you can do it by using the energy estimate, using the spectral decomposition, you can use by maximum comparison principle, etc. And then the third part is that you try to solve the finite dimensional problem. And this part, you will specify the choice of initial data. Okay, let me try to explain what is the first step. So the first step, what is approximate solution? So this is an approximate solution. So we have the leading term is still the stationary solution, the rescale stationary solution. Here nu is the unknown parameter. And we have some kind of modification that driving the law of the plot. So here phi L, phi 0 is the eigenfunction of the linearized operator. And AL is some parameter. And here we have the phi L is the radial eigenfunction, so corresponding to eigenvalues. We have some log correction here. And basically that this one is the singular limit eigenproblem, in the sense that when you take nu to go to 0, the eigenvalue of the limiting problem is completely different with its value. Exactly that when you take nu go to 0, so the eigenvalue is given by -1 minus n instead of 1 minus n. So this is so-called the singular limit eigenproblem. And also this eigenproblem is a two-scale problem. And to obtain information, we use the partial mass setting, we use the machine and synthetic expansion, and we also use the Sturm-Liouville, classical theory. So that's the first part. We are able to obtain a good approximate solution. And to control the remainder, we need to understand better the linearized operator. So the linearized operator of the Keller-Segel, for the 2D Keller-Segel, it looks like this one. Actually, that we can read it. We can write them in the divergent form. And this structure is natural because it's coming from the linearization of energy functional. So when you study, if you want to study the linearized operator, so usually that at the original problem, you also have some kind of energy structure. And then the linearized operator, you should derive from that linearize, you should linearize the energy structure, the energy functional. And then you will obtain the correct structures of the linearized operator. And from that, you can easily obtain what is the space you need to consider. You need to study the linearized operator. And here we have the linear operator M here is coercive in up to some orthogonal condition. So this one, which is enough for us to perform the energy estimate. Okay, so we have the first step, we have the good approximate solution. How can we obtain the law of the Prof? So we have, you see, when you use the spectral decomposition, you just project the answer, you just plug this answer to the equation W here, and then you project it on the eigenmode phi out, and then you will simply obtain this ODE satisfied by nu. So this is the advantage of our approach, is that to simplify the way to obtain the law of the Prof. And we have for the KL equal to 1, it's given by this ODE. For L greater than 2, we have this ODE. And you solve it, sorry. And when you solve it, you will obtain the law that you show you in the theorem. And here, what you see here, we have the error, the epsilon, the radiation. The error here, we need to be of sine nu square over log nu square. So which is the typical size that we could not do better. So when you control approximate solution, you have to make sure that the general error have to be of this size. Otherwise, you cannot close the equation satisfied by nu. Okay, so how can we control the remainder? So the basic idea is that we just decompose the solution, the radiation epsilon, into two parts, the radial part and the non-radial part. For the radial part, because we know the spectrum, the spectrum, the linear operator in the radial sector, so we can use the spectral decomposition to control the solution in the radial sector. And for the non-radial part, we use the dissipation because we are dealing with the parametric equation, and then we have the dissipation structures, and then we have the coercivity estimate of linear operator. And this coercivity estimate is mainly related on this inner product. And this inner product is natural, coming from the linearized energy functional. Right. So this is the idea, how can we use to control the radiation and remainder. And yeah, that is the main idea for the single Prof construction. Okay, so let me show you how can we use that idea for the multiple, collapse construction. Before that, what do we have is that there's some results on this multiple soliton. So they are the work by Keller-Segel and Raphael for the 3D Hak-3 equation, and by Martin and Merck for the two soliton collision for the GKDV, and we also have the work by Raphael and Jacques in multiple soliton for energy subcritical nonlinear wave, and we have many others work. So the most of similar results with what I will show you is the construction of Martin and Raphael for the qubit nonlinear Schrodinger equation. But in their work, they construct an infinite time Prof solution, where the profile here, the nonlinear profile Q here, have the exponential decays, so that the interaction between the soliton is weak, so that the leading dynamic, the length scale here, it doesn't change. And then we have the nonlinear. We know that the nonlinear Schrodinger equation, we have the pseudo-conformal symmetry, so that after this transformation, we will have the finite time Prof solution, but which is artificial. But the analysis is mainly based on the infinite time Prof analysis. So what we did is that we are able to construct precisely the initial data is still with the finite mass and in the energies R2s. so that the solution can be decomposed at the leading order, the sum of two solitons and plus the radiation. Of course, here we have to understand better what is the radiation here to be able to compute the length scale lambda here. Here capital Q is still the nonlinear, the stationary solution. The distance A here, we have one more addition parameter is that the A, the distance between the two solitons is equal to 2. And the length scale is different from the single block construction. And you can see here that the total mass concentrate at one point is given by 60 pi. So we do have the case that the solution concentrate which is greater than A pi. So for the single block construction we have, for the single block we only have the concentration of A pi. And the law here, the gamma 1 here equal to 1/2. But here gamma 1 is some positive constant, depend on the number of the soliton you put here. Okay, so there's some issues arise in the analysis for the multiple collapsing construction. So mainly the first issue is mainly coming from the decays, the polynomial decay of the stationary solution. And then because this polynomial decays, so it will create a strong interaction between the two solitons. And it will change the law of the Prof. The second issue is that the linear operator is completely non-real. There's no way to use the partial mass setting to remove the non-local effect in the linear operator. So we have to deal with the completely non-real operator. And still the same, the linear operator is a multiple scale problem. And the third issue is that the sum of two soliton is no longer an exact solution. Remember that for the single block construction we have this exact stationary solution. But here, when you put a sum, it's no longer the exact stationary solution. We have to find a way to improve it. And the next issue is we use the energy estimate. When you want to perform some kind of energy estimate, you need some kind of spectral gap or some kind of the coercivity. But here the coercivity estimate here is not only rely on the perturbation argument, but there is require some crucial identity. And we have the last issue in terms of technical difficulty is the L1 criticality, that we need a careful treatment for the nonlinear at the nonlinear level. So in terms of nonlinear PDE, when you linearize the problem around a nonlinear object, so usually the radiation, it will behave like the solution of linearized equation, and you can neglect the nonlinearity. But here for this case, because we are working on the L1 criticality, so the nonlinear term have certain crucial size that contribute, that affect to the dynamic of the solution. So that we need to be careful here. Okay, so the main idea is that we still work on the self-similar variable, which is the equation W. And in this setting, the theorem is equivalent to the following, that we try to construct initial data for this equation so that the solution exists globally in time and decompose at a sum of two soliton plus a radiation. So in this setting we have the concentration near, so the solution is concentrated at two different points, and the distance of 2 points is equal to 2. So in the zone that for Z is less than to any power eta, we have the 60 pi, but close to the concentration point, we only have the concentration A pi. So the main task is that we need to compute precisely what is the radiation here. So foremost speaking is that how can we compute the radiation epsilon? So I call it the correction. So the correction here is coming from two sources. The first one, we have the cell interaction, because when you look at the Keller-Segel here, we have a nonlinearity here, we have the non-local effect, so we'll create the cell interaction. And we also have the effect of this guy transfer to this guy. So there are two measures of effect that you need to compute to be able to characterize the correction here. And the distance here, A is here equal to 2, is to eliminate at the leading order term the effect of the second purple to this guy. And here, how can we compute the length scale nu here? Okay, so the first step, we try to make a good approximate solution. And how can we do it? So if you remember the single plug construction, we want to compute approximate solution by using the eigenfunction. And here, because you know the linear operator around the two solitons is quite complicated, and we are not able to compute the full spectrum of the linear operator, but we are able to compute the approximate eigenfunction. So in the sense that there exist two eigenfunctions of the linear operator, such that the error, so the error here of this side, this is the typical side, nu square over log nu square. And this one is the approximate eigenvalue. Of course here the eigenfunction here is completely non-radial, and it can be decomposed the inner part and the outer part. I will explain to you later. And there's the gamma one. The gamma one is positive constant, is enter to the law of the Prof here. Just here. Okay. So I think that I should skip this one. So this is some kind of structure of the approximate eigenfunction, but you need to not worry about that too much. There are certain calculation you need to carry out to be able to compute the leading order of the inner approximate solution and outer approximate solution. And it's quite boring calculation, and we have to use computer to help at some step. And the outer approximate eigenfunction is we need to deal with some kind of Fokker-Plonk equation operator with some singular potential here. And here the singular potential is located at two different points. And the distance here, A equal to 2, is the crucial to obtain this asymptotic behavior to be matched with the inner approximate solution. Okay, so we have another issue is that, remember that the sum of two solutions is no longer the exact solution. So here we have to find a way to improve it. And what we do is that there is a small function s, so that when you add to the sum of two solutions, it can improve the error. Actually, the error is not improved, but you can connect it to the error, can be connected to the first eigenfunction. And the next term's error here is of the size you want, which is nu square over log nu square. So that is unavoidable. You have to find a way to do it. And now you have, at this stage, you have almost everything. You have a good approximate at a steady state. You have a good approximate eigenfunction. And now how can you build approximate the whole approximate solution? And here, this is the approximate solution. So the leading order term is given by the correction. So remember that the sum of two solutions is no longer the exact solution, so you need to improve it. So this is the improved steady state. And then we have this one, the subtraction of the two eigenfunctions. And then when you plug in this answer to the equation here, and then you will obtain certain, ODEs. And then where the side here, see here, the side here, the error is a typical sine nu square over log nu square. And then you project it on the eigenmode and you will obtain this ODE, and from that you can solve it with this compatibility condition. You will get the law of nu, which is given by this one. And here the value, the approximate eigenvalue gamma 1 is important, which is positive here. All right, so at this stage we have the approximate solution. We know how to determine the law of the Prof. And the next step is how can we control the remainder. So to control the remainder, we need to understand the linear operator. And if you want to perform the energy estimate, so the one way that you need to have some kind of spectral graph or the coercivity estimate of the linear operator. And when you want to prove certain coercivity estimate of the linear operator, you need to know what kind of functional space you're working on. And this is one thing, and the second thing that is depend on the scalar product you consider. Right. There are two things. And here we're working on this. We're working on the L2 space with it in the product. And remember that this one is the operator M here is natural coming from the linearization of the energy functional. But here it's around the two soliton. And then what we obtain is that when a distance of two soliton in the self-similar setting is fixed equal to 2, and when a parameter nu is small, so that up to some local orthogonal condition, we have certain coercivity estimate. And with this kind of coercivity estimate, you are able to perform the energy estimate to close the linear analysis. But there are problems with this coercivity. You see, the coercivity estimate here is in terms of local orthogonal condition. And the modulation equation here is some kind of related to the global object. So how can we link the two things? Because if you don't find a way to link, some kind of local object and with the global object, you will like, a snake eat the tail. So we have to find a way to connect the two objects, the global and the local objects. For that, we use to further the composition of the solution. And here, the adapt, in the product, it play a crucial role to make certain, cancellation. And here, the cancellation here is not much. It's only 1 over log nu, but it's okay. It's enough for us to close the analysis. So let me summarize some key ideas for the multiple collapse construction. So we work on the self-similar variable. And then the first issue that we can improve the sticky state here. And here the distance A equal to 2 is crucial in this refinement. And the second issue is that we know we are not able to compute the whole spectrum linear operator, but we are able to compute some approximate eigenfunction of linear operator up to some small error. And we are able to prove the coercivity estimate of the linear operator under this adapted inner product. Of course, this one is crucial because it's coming from the linearization of the energy functional. And then when we have it, we put a projection. We obtain the law of the nu of the length scale by projection of the ansatz on the eigenmode. And we also need to use the crucial step, the further decomposition to connect the local object with the global object, so that we are able to control the solution in the whole space. So that is some kind of key idea we need to use in our multiple collapse construction. So that is for 2D case. So 2D case we have single Prof solution, we have the multiple collapsing blob solution. And how about the 3D case or higher dimensional case? So we have that for dimension d greater than 3, we have the blob solution of this form, which is the constant. At first, the incinerator concentrates on the surface of sphere, and the radius capital R is screened to 0 when t approach capital T, and the length scale lambda here is related to the radius of radius capital R here. So basically, that this relation is to make sure that the solution we construct have the finite mass blob solution. And because for d greater than t, we are in the L1 supercritical, so in the sense that if we are able to construct a finite time blob solution with a positive mass, we are able to use the scaling invariant here to have a blob solution with arbitrary mass. And the solution we construct is stable under perturbation in this set. So these are the formal pictures of what we did in the radial setting. So you see the solution is concentrated with a distance capital R here, and the concentration here is a lambda. And by the scaling invariant of problem, so if the concentration is lambda here, so the height of the solution has to be 1 over lambda squared. And when you compute the total mass of the solution, it will give you this relation. The capital R, lambda have to be related to the capital R to the power d minus 1. That to make sure that we have the finite mass blob solution. And then the solution is moved to 0 here, because capital R go to 0. So what interesting thing here in this blob construction is that the profile W here is connected to the viscous Berger, the 1D viscous Berger profile. So that's the thing interesting we found in our construction. And in dimension 3, we also found another kind of blob solution, which is given by this one, or the non-zero blob profile given by this one. So this one is still ongoing, but we are almost finished. And to obtain such a kind of blob solution, we require the computer assistant to solve certain nonlinear system of ODEs that I believe that if we do it by hand, it will take more than a month. And I'm not sure that without errors. And more detail about the inner structure of that kind of such solution is that we have this inner expansion. For the radial blob solution and for the non-radial blob solution, we have this inner expansion. So in the self-similar setting. And basically that to obtain such this one coming from solving this nonlinear ODEs. And to obtain this system, we use the computer assistant to help us to make some projection. Not some projection, but many projections. And it turns out that there are two exact solutions. One corresponding to the non-radial blob solution, and another one is corresponding to the radial blob solution. And so let me finish my talk today by some conclusion. So we are able to use the spectral approach for the blob construction for the 2D case, and the linear operator is associated to the multiple scale problem. And we also have the real construction for a blob mechanism formed by the collision. So we have the multiple collapse phenomena. And this is the first, in our knowledge, this is one of the first time ever this construction happened. And we also many different kind of blob pattern for the higher dimensional case. We had a collapsing ring blob solution, we had a Taiwan lock, and maybe other kind of blob solution. And when you see here, for the Keller-Segel equation, we have many kind of blob solution that can appear. And how can we obtain the classification of all possible blob pattern? So, which is a long-term project we are going to do. Yeah, thank you for your attention.
So, any questions or comments?
Sorry, I don't familiar with progress. I would like to ask why we need to study blowout solution to PDEs.
That's a very good question. That when I start, to study, when my previous, my supervisor gave me just a project, I also asked the same question. And actually, that for me, from my understanding, that to study such a similarity in PDEs is to prove that the mathematical model we are studying is valid or not. For example, for the 2D Keller-Segel, we start with smooth initial data. So we have the concentration phenomenon. But after that, the solution is bounced up and we cannot define the solution after that. And then this means that the model is no longer valid after that time. And we need to modify or we need to make some adjustment to the model, to the mathematical model we are studying. So that is one explanation that I get from my supervisor.
Thank you.
And also that in terms of application and in terms of mathematical studies, finite time block or global in-time assistant is equivalent because after one chain of variable, you will convert the study of finite time block solution to a long-term unsynthetic behavior. And then the long-term unsynthetic behavior is one of the main object study in nonlinear PDE. This is another example. So the similarity of finite time block is measured in them. So after changing the variable, we all study the long-term unsynthetic behavior of the solution. I hope I answered your question.
So I have a question. So does this kind of system, connect to real-world scenario directly?
Actually, that because the name of Keller-Segel is proposed by Keller-Segel in 1971 or 1973, and then many modification of this model by modify the second equation, by modify the nonlinearity. But for me, that I just focus on pure mathematical analysis. So I don't care much about the really real application. Yeah.
I see. Thank you for the answer.
In this model, this calculation, are it possible to scaling the velocity to the different velocity to the blow-up point, 2 point, but with different velocity?
You mean for the multiple blow-up solution, right?
Yeah.
That's possible if you consider the multiple blow-up. So we have. So if you consider the non-interaction, so if you have the one block here and another block here very far away and don't have enough time to interact, so yes, my answer is yes, you can construct a block solution here with a different block speed, and here with a completely different block speed. That's possible. That is just a contribution. But in terms of interaction, if the multiple for the two solutions they interact, it's very difficult to make it a different landscape because it's will related to the distance and the concentration speed. And for me, that's doable, but it will add some more parameter to the system, and I don't think that it's easy to solve, but it's possible in my opinion.
Okay, so if there is no further question, let's thank Tien for his wonderful talk.